Hello, I'm going to assume that you already know the basics before jumping into this video, meaning you know how to differentiate and to integrate, and you have a large idea about the tests, which I'm going to insert right over there. I'm going to assume that you have covered up tests of divergence and convergence, and that is some of these things. This one is an example. Also, the integral tests, like that. And then I'm going to assume that you already know about the geometric series, harmonic series, P series, and comparison tests. You can feel free to pause and see my notes and take note about it. Limit comparison test. And now we're going to jump into the ratio test. We can know that the series is absolute convergent and divergent based from these things, as you can see. And I'm going to assume that you know that already. The root test. There. For differentiating and integrating power series, those tests for convergence is important. We are going to review what is a power series. How are we going to determine if it is a power series? As stated here, I have put it here. As you can see, this series, it is like that. Now, as you can see, there must be a variable, a coefficient, meaning the coefficient is the number before the variable, that is the x, and there is a power sign over there. Now, for differentiation and integration of power series, the sum of power series is the function, meaning look at this set of series, and the sum of this power series is the function f of x, as we have put it here, and whose domain is the interval of convergence of the series. Here the center is x minus a inside those parentheses. We would like to be able to differentiate and integrate such functions, as stated in the title. And following the theorem, which we won't prove, says that we can do so by differentiating and integrating each individual term in the series, just as we would for a polynomial. This is called term-by-term differentiation and integration. If the power series here, summation of c sub n, and the quantity of x minus a raised to n has a radius of convergence, r is greater than 0. The radius, however, remains the same, but the interval of convergence does not mean that it stays the same. Remember that. The radius of convergence stays the same as stated here in Theorem 2, and then the interval of convergence, however, does not mean that it remains the same, meaning it is prone to changes. That is why we have to see it. Now when everything is being met, for the power series of with the summation c sub n, the quantity of x minus a raised to n, and has a radius of convergence r that is greater than 0 and can be defined in a function of f of x with the following series and this following summation. And now the sum of the power series becomes a function, and it meets all the qualities that can be continuous and can be therefore differentiated and integrated. Now for the first example, I have here an example from my favorite tutor coming from the YouTube. As we can see here, he has the function f of x equal to the summation of x raised to n over n factorial, and he is going to differentiate and integrate it. So here is the f prime of x. As we can see, he did not differentiate the n factorial because that is a constant. He's just going to differentiate the x raised to n. And to integrate, he has the antiderivative of f of x dx, and he did not integrate the n factorial as well. And that are the final answers. For another example, you may look at this example from him. For a little bit of challenge, you may look at this third example coming from him and finding the intervals of convergence of f of x, f prime of x, and the indefinite integral. Make sure that you remember the ratio tests and the geometric series that you have learned from before jumping into these questions. We are now jumping into the examples from the book from James Stewart. And for example number 4, now we have the function of j sub 0 of x equal to the summation of negative 1 raised to n times x raised to 2n over 2 raised to 2n times n factorial squared. So to differentiate that, we don't need to differentiate negative 1 raised to n, 2 raised to 2n, and n factorial because these are constants. So the derivative of x raised to 2n is 2n times x raised to 2n minus 1, and as we can see from the photo, that is the final answer. Aside from questions asking to differentiate and integrate, some questions also ask about intervals of convergence, and as well as this one from example 7 and example number 6. And it talks about the power series representation, and it has to be manipulated and can be discussed in some other videos like this one from Patrick JMT from YouTube. And the last example that I am going to talk about in this video is the example 7. Find a power series representation for f of x equal to arctan of x. So we have observed that the f prime of x is equal to 1 over 1 plus x squared. It means that is the key observation for arctan x. And it is manipulated, and from this question, we have to find the required series by integrating the power series for 1 over 1 plus x squared. Now, arctan of x is equal to the integral of 1 over 1 plus x squared dx. And finally, it has come up with c plus x minus x cubed over 3 plus x raised to 5 over 5 minus x raised to 7 over 7. And finally, it has come up with this power series representation with the summation of negative 1 raised to n multiplied to x raised to 2n plus 1 over 2n plus 1. And since c, it can be put with x equal to 0, can obtain c is equal to arctan of 0, which is equal to 0. And since the radius of conversion of the series for 1 over 1 plus x squared is equal to 1, then the radius of convergence for this series for arctan x is also 1, as I have discussed that the radius of conversion does not change, unlike intervals of convergence. We have learned from this video as much as I did. So that's all. And keep learning, keep safe, and keep healthy.